Yes, Meera Upasana, I'm audible.
Yes, sir.
Yes.
Okay, so in the last class, we have done up to this electric field due to a line charge, right? That was the last
Yes,
topic.
sir.
Okay. So along with the line charge, now we'll discuss electric field due to a circular wire, a coil. And the coil we're discussing, circular coil, semicircular coil, a quarter coil. Then we will do the combination of the straight wire and the circular coil. So let's start. So electric field due to a quarter circuit. Electric field at center of a quarter circular coil. Center of quarter circular coil. So once you know the result of the quarter circular coil, you can repeat this result to get the electric field due to a semicircular coil and a full circle coil. So if you have a quarter circle, so this is quarter circle. This have some positive charge. Linear charge density is lambda. Radius of the circle is r. You are supposed to calculate electric field at the center of the center of the quarter circle. So at the center of the circle, this will have two components of electric field. One is the x component, another is the y component. The value of both x and y component is lambda by 4 pi epsilon naught r. It's lambda by 4 pi epsilon naught r. And EY is again lambda by 4 pi epsilon. In the problem of quarter circle, magnitude is easy, like you can easily remember this formula. But the issue is with the direction. So what we can do is, instead of taking the complete circle, to get the idea of the direction, whether the field is along positive x-axis or it's along negative x-axis. The field is along positive y-axis or it's along negative y-axis. To get this idea, what we do, we take a small element here, small element, let's charge over the small element is dq. If the linear charge density is positive, the charge over the small element is positive, and the direction of field is this. This is the direction of field. Now, if you take component of this dE, one component will act along x-axis, another component will act along y-axis. So we'll have both the x component. So the x component will be along positive x-axis, and the y component is along negative y-axis in the downward direction. But instead of this positive charge density, in the same case, if I take a quarter circle with a negative charge density, let's say this have a negative charge density, and I want to calculate the field here. The magnitudes will not change. Magnitude will be lambda by 4 pi epsilon naught r and lambda by 4 pi epsilon naught r. But the challenge is the direction. If you take a small element here, then what is the direction of the field? It's away from the charge or towards the charge? Upasana. If I take this small element dq towards the charge.
Towards.
So Meera, what would be the components? What would be the direction of the components of field? Positive x, negative x, positive y, negative y. Meera,
Negative y-axis.
no. See, this is dE, right? So if you take the y component of dE, this will be upwards. This is ui. And where would be the negative x component? The x component of the field. Positive x-axis or negative x-axis?
Negative x-axis.
Negative x-axis. So see, the directions of field are reversed. So that is the major task for the quarter circle. You have to decide the direction of the field. Once you know the direction, then it's easy. Both the magnitudes are same. It's lambda by 4 pi epsilon naught r. Lambda by 4 pi epsilon. You can easily connect it with the semi-infinite wire also. For the semi-infinite wire, also the expression of field was same, lambda by 4 pi epsilon. Now let's do a very simple problem on this concept. Let's take a semicircular coil. In this semicircular coil, instead of a single charge density, let's put two different charge densities. One is the positive charge density lambda. Another is the negative charge density, which is minus lambda. This is plus lambda and this is minus lambda. You're supposed to calculate the electric field at the center. So in a semicircle, you can easily divide this semicircle into two circles, right? There are two circles. There are two quarter circles. So let's name it as 1 and name it as 2. If we follow the rules for the direction, then for the first one, the small element will be here. So the x component of field is positive x-axis, that is Ex due to first component. Y component of field will be downward. So this is Ey due to 1. If I take this small element again, this is negative. Direction of field due to this negative will be towards the coil. So the x component will be along negative x-axis, that is Ex2. And y component is again downwards, it's Ey. So if you're supposed to calculate the field, net field along x-axis is, see, this Ex1 and Ex2, they are acting in opposite direction. So Pasta will add them up or they will get subtracted.
Subtract.
What would be the magnitude of Ex1 and Ex2? It's lambda over 4 pi epsilon naught, right? Ex2 is again same. Both the quarter circles have same linear charge density and the same radius. The only difference is in the nature. One have positive charge, another have negative charge. So it's lambda by 4 pi epsilon naught r, lambda by 4 pi epsilon naught r. They will cancel out each other. Ex will be 0. Similarly, if I calculate Ey, Mira, for Ey, we'll subtract them or add them?
We'll add them.
So that is Ey1 plus Ey2. So that's lambda by 4 pi epsilon naught r, lambda over 4 pi epsilon naught r plus lambda by 4 pi epsilon naught r. So that comes out to be lambda by 2 pi epsilon. So instead of this type of semicircle having two different linear charge densities, you can get a simple semicircle also which have the same charge density. In that case, that's a standard formula, electric field at center of semicircle. So you have a semicircular arc and you're supposed to calculate field at the center. The charge density is positive throughout. So what happened here, if you apply the same concept, then field due to the upper quarter and the lower quarter, the y component of field will get cancelled out. But the x component will get added up. This is Ex1. Similarly, this is Ex2. So the net field along x-axis is Ex1 plus Ex2. So that is lambda by 4 pi epsilon naught r plus lambda by 4 pi epsilon naught r. That will comes out to be lambda by 2 pi epsilon. So on linear charge density, you can get these two types of problems. Although in NCERT, these topics are not mentioned in NCERT, but you will get these in the PYQ of JEE. You can't leave those topics. Okay, if you want, just note it down. Then move on to the electric field on the axis of a coil. Yes, written.
Yes, sir.
Yes, sir.
So after this semicircle, if you come to the complete circle, like electric field at center of circular coil, at center of circular coil. So using symmetry arguments, you can decide what should be the value of electric field at the center. The symmetrical system, electric field at the center will be 0. So for a complete circle, field at the center is 0. Now there is another topic which says electric field at axis of coil, circular. Now if you take a circular coil, over the circular coil, the distributed charge is Q, radius of the coil is R, and you're supposed to calculate field at a point on the axis. The field over this point is, it's KQX over R square plus X square to the power 3. This is the expression of electric field on the axis of circle. And the direction of field, if the charge over the coil is positive, then the direction of field is away from the charge. And if charge over the coil is negative, then the direction will get reversed. The direction will be towards the coil. So this is the electric field at axis of the circular coil. You can even plot it. If using this expression, if I want to calculate the value of field at the center, Upasana, what would be the value of X at center?
At center, X will be 0. So it will be
X will be 0. So your field will be 0. The same result that we write. Now, you can even plot the variation of field with position for the point on the axis. So this is the center. Here your X is equal to 0. At the center, field is 0. And if we go to the positive x-axis, X increases. So there will be a point where the field will be maximum. And then it will gradually decrease. And at X equal to infinity, it will approach to 0. At center, it's 0. Similarly here, if you want to get the value of field here, the direction will be to the left. Left means your field is negative. We are plotting your field on the y-axis. Field is negative means we'll plot it along negative y-axis. So here also. Now these are the points at which field is maximum. If you're interested in calculating this point, that you can easily calculate using max min. And maximum minima, what you can do is you can differentiate E with respect to X and then equate it to 0. So when you equate it to 0, you can get the value of X. That value of X is plus minus R by root. So the value of the field is maximum at plus R by root 2 and minus R by root. This plot is important. Just note it down, then we'll move on to the electric field lines. Tell me once you have written.
done.
After this point, electric field at axis of circular coil, the next is, okay, after circular coil in wire, the next shape is sphere. Hollow sphere and the solid sphere. Hollow and solid sphere we'll do with Gauss law. We'll derive the electric field using Gauss law. Now we'll move on to electric field lines. Okay, that's a very theoretical topic. If you remember all properties, then we can directly jump to numericals. Electric field lines. Vasna, just keep telling me the properties of electric field lines. If I have an electric field lines, how will you get the direction of electric field?
Positive to negative.
Sorry?
It starts from positive to negative.
No, no. If you have a field line, then the direction of field is tangential to the field line, right?
Tangent. Yes.
And yes, it starts from a positive charge and it terminates at a negative charge. The next important property is that of a neutral property of neutral point. So what is neutral point? Neutral point is the point at which net field is zero. So point at which net electric field is zero is neutral point. So at neutral point, what happens? Near the neutral points, field lines are parallel. Field lines can never cross the neutral point. So if I take a positive charge Q1 and I take a charge plus Q2, and I say that Q1 is less than Q2, Q1 is a smaller charge, so the neutral point will lie near the smaller charge. When you draw the field lines, you have to take in care of various things like positive charge. The field lines will start from the positive charge and terminates at infinity. This is again a positive charge. Field line will start from this positive charge and terminate at infinity. Field lines can never cross the neutral point. Near the neutral point, field lines are parallel. And you also have to take care of the number of field lines. For the smaller charge Q1, the number of field lines is small. For the comparative greater charge Q2, you have to draw more number of field lines. So what you will do here is, this is Q1, this is Q1. Field lines are parallel near the neutral point. This is Q2, this is Q2. But since Q2 is greater than Q1, I'm drawing 5 field lines for Q2 and just 3 field lines for Q1. This is it. After neutral point, the next important thing is if you have a conductor, what is the property of conductor here, Meera? There is some specific property for conductor.
Charge lies on the surface.
Charge line on the surface. And what about the electric field lines? Can they penetrate a conductor? No.
No, sir.
Field lines cannot penetrate a conductor. They are always perpendicular to the surface of the conductor. And just remember, if you have a spherical conductor, then this normal on the sphere is this line. Radial lines are normal to the sphere. These lines are perpendicular. Okay, so these are the properties. Just you have written this thing, na? Electric field line on the axis of a circular
Yes,
coil.
sir.
Do you want to note this thing also, the properties of electric field lines, or remember them? Okay, if you want, you can note it down. Let's do it first. Then we'll come to numericals on field lines. So I'm not writing those properties that they start from a positive charge, terminate at a negative charge. If there is attraction, then field lines will contract. For repulsion, they will exert lateral pressure over each other. All these properties you can see here. Tell me once you have written, move on the next one.
Done, sir.
Now let's move on to the numericals. So give me 1 second. There is one more numerical on field lines. Yeah, is this visible? Yes,
Yes,
is this
sir.
question visible? Okay.
Yes.
So these are the field lines for 2-point charges as shown. Sorry. So first of all, you have to decide which charge is okay. Is the field uniform or non-uniform? Can you decide just by looking at this field lines? Field is uniform or non-uniform? See, for uniform field lines are straight and parallel. If they are not straight and parallel, that means field is not uniform. So the answer is it's a non-uniform field. The field is non-uniform. If you have a uniform field means both magnitude as well as direction of field will not change. Then the field lines will be parallel, equidistant field lines. Then you need the ratio of QA and QB. So to get the ratio of QA and QB, you just have to count the number of field lines. Say for A, you have 1, 2, 3, 4, 5, 6, 4 here, 4 here, 8, and 4 here, 12 field lines. Divided. If you want to get the value of charge B, then just count the field lines. 3 and 3, 6 here. So the ratio of charge is 2:1. Means QA is double of that of charge. What are the signs of QA and QB? Basna, can you decide whether A is positive or negative?
A is positive.
A is positive, field lines terminate from a positive charge and they starts from a positive charge and terminate at a negative charge. Apart from infinity, where is the neutral point? Can you find neutral point anywhere?
D.
D.
Not D. Near D, field lines are not parallel. Near the neutral point, field lines are always parallel. They are parallel at E.
E.
So the neutral point is E. We can skip this question for the time. Where will the lines meet which are coming from A and not meeting at QB? These are the lines. These lines which are coming from A, but they are not going into B. Where are they going? They are going to infinity. They are going to infinity. Will a positive charge follow the line of force if free to move? Yes. A positive charge will follow the field lines or they move along the tangential direction. Like if you have a field line and I leave a positive charge here, in which direction this positive charge will go? It will go along the field line, it will go tangential to the field. Yes, Meera.
Tangential to the field line.
Tangential, because positive line goes, charge goes in the direction of electric field. So these are the type of questions that you can give, because in MCQs, you're not going to draw the field line. So these are the questions that one can get. Please note it down. It's an important question. Done?
Done.
Sure. Now, after field lines, the next topic is path of charge particle in electric field, like how field lines will exert force on a charge particle. So the next is force on charge particle. Force on a charge particle in external electric field. So if you have an electric field, this electric field is E, and in this electric field you placed a charge Q. This charge Q will experience some force, and that force is QE. The direction of force is same as that of electric field if your charge is positive. But if your charge particle is negative, then it will experience the same force in a direction opposite to that of electric. The magnitude would be same, QE. So for both the positive as well as for the negative charge, the direction of force, the magnitude of force is same, it's just QE. But if the charge is positive, it will go into the direction of field. And if charge is negative, it will go in opposite direction of that of field. Now, once you have this force, the whole question is of kinematics. After force, you can calculate acceleration. What is acceleration? It's QE by m. Now, if this acceleration is uniform, or after this acceleration, you can get two type of problem, one-dimensional problem and two-dimensional problem. One-dimensional problem will match with class 11 topic motion in straight line. Two-dimensional problem will match with projectile motion. So if you have one-dimensional, then you will be using these type of equations. In two-dimensional, you will be using the relations which were for projectile motion. We'll discuss this in numericals. So if you place a charge particle in an electric field, it will experience this force, it will experience, this will have this much of acceleration. Then you can have two types of problem on 1D and problem. Just note it down, we'll do both the type of problems. Yes, written.
Done, sir.
Now for the 1D problem, the 1D problems are easy. For one-dimensional problem, there's one problem in NCERT, solid example of NCERT. Two plates are given. One of the plate is positively charged, another plate is negatively charged. The charge density is sigma and charge density is minus sigma. You can consider these two plates as the plates of the capacitor. So there should be an electric field from the positive plate to the negative plate. Let's call that field is E. Yes, do you remember what is the expression of this field between the plates of capacitor if they have charge density plus minus sigma? Electric field between the plates of capacitor is sigma by epsilon. Now in this plate, between these two plates, it placed a charge Q, positive charge Q. This charge have a mass M. You're supposed to calculate the acceleration, the displacement, velocity and everything. So let's first calculate the force on the charge particle. Force is QE. It's Q sigma by epsilon naught. That is the force on the charge particle. What is the direction of force? It's a positively charged particles. The direction of force is same as that of electric field. Then you have acceleration. Acceleration is force by mass QE by m. So this is Q sigma by epsilon naught into m. That's the acceleration. Now, this field is usually uniform between the plates of capacitor. The field is uniform. Means this acceleration is uniform. If this acceleration is uniform, then you can calculate various things. Like you can calculate velocity with which it will strike the another plate. To get that velocity, you can use this equation V is U plus 8. Or it can ask you to calculate the displacement. Displacement is ut plus half at square. Or it can ask you to calculate velocity when time is not given. Then use this equation. Now, once you have acceleration, you can use these three equations to get the desired quantity. These are one-dimensional problems on force on a charged particle in electric field. Note it down. They will do one numerical on two-dimensional. This is a solid example of NCERT also. In NCERT, instead of charge density, electric field is given. But if you look at PYQ, then the charge density is given. So first you have to calculate the electric field and then force. Yes, written.
Yes, sir.
Sure. Let's move on to a two-dimensional problem. Yeah, solve this problem. Do it. First, note down the question, solve it. You have 3 minutes for this question. After 3 minutes, I'll start solving. So the hint is first calculate the values of velocities. Like first calculate the x component of velocity, then calculate the y component of velocity. Tan theta will be simply Vy by Vx. Aji, written? Answers? Upasana? Mira, answers? Okay, if you're not getting any answer, let's solve it together. See, a particle is entering in between two plates parallel to x-axis. The direction of field is along y-axis. And the particle is electron, negatively charged particle. Field is downwards. So when the electron enters into the field, Upasana, what will be the direction of force? Electron will experience force in the downwards direction and the upwards direction.
Upwards.
Upwards, because it's a negatively charged particle. Good. So that's the force. Now let's divide its motion into two parts, x-axis and along y-axis. Because the particle is going along x-axis, but force is acting along y-axis. So it will not go in a straight line. The path will be parabolic. So along x-axis, there is no field, so no force is acting on the particle. Initial velocity along x-axis is v0. If there is no force along x-axis, that means there is no acceleration along x-axis. If there is no acceleration, that means velocity along x-axis will remain constant. There is no change in velocity along x-axis. Now let's come to y-axis. So along y-axis, there is a force that you can calculate EE, where E is the charge of electron and capital E is the electric field. Initial velocity along y-axis 0. There's nothing along y-axis. Acceleration along y-axis is EE by mass of electron. Next, when an electron moves from one plate to another, what is the distance that this electron covered along x-axis, Mira? From here to here, when the electron did L. So
L.
if you have distance, you can calculate the time, I believe. And if I use this equation, x is uxt plus half axt square. So your x is equal to L. Your ux is v0, time is t, ax is 0. So you can write that your t is, it's L by v0. So this is the time the particle will take to move from one end of plate to another plate. In the same time, the velocity of particle Vy can be calculated as Vy is Uy plus Ayt. You can say that Vy is Uy, Uy is 0, Ay is E by mass of electron into T, which is L by V. So this is Vy. Vy is, it's EEL by mass of electron into V. This is Vy and this is Vx, which is V. Now you're supposed to calculate tan theta. See, if this is the right angle triangle, this is Vx, this is Vy, this angle is theta, then tan theta is perpendicular upon base. You can write that tan theta is Vy divided by Vx. Vy is EEL by mv0 and Vx is v0. So this is EEL by mv0 square, that's tan theta. So once you have tan theta, you can write your theta as tan inverse EEL by mv0 square. So that's a two-dimensional problem with the same concept. Note it down. Mira, can you calculate displacement covered by the electron along y-axis? Although it's not into the question, but if it asks you to calculate displacement along y-axis. So this electron from here, it's going here. So there is a displacement along y-axis also. So can you calculate that displacement along y-axis? Upasana? This is velocity along y-axis. Can you calculate displacement along y-axis?
Velocity by time.
velocity into time is valid only if acceleration is 0. If there is an acceleration, then you have to use equations of motion. So which equation you will use?
So we have to use S is equal to ut plus half at square.
Yeah, so we'll be using y is uyt plus half ay t square. So you have uy, which is equal to 0. You have ay, which is e by m. Then you have t, which is l by v. So this is how you can calculate displacement also. The same problem is in 2 NCERT. In the chapter 1, in the back exercise of NCERT, it's the last question or second last question. But in NCERT, instead of theta, it's asking y, displacement covered along y-axis. Yes, written.
Then
Next, let's discuss dipole in uniformity. Now, instead of charged particle, if I place an electric dipole in uniformity, electric dipole in uniformity. So if instead of a charged particle, this is uniform field. And in this uniform field, I placed a dipole. I placed a dipole having charge minus q and charge plus q. Length of the dipole is 2. So what happened here is, this is electric field E. The positive charge will experience a force QE in the direction of field. Negative charge will experience the same force but in opposite direction. So the net force on the dipole will be, the net force on the dipole is, it's QE minus QE. So these two will cancel out each other and you will get that the net force is 0. Net force is 0, that means your dipole is in translational equilibrium. Your dipole is in translational equilibrium. So translational equilibrium means not going into the straight direction, means neither it can go along positive x-axis nor along negative x-axis. It will not have translational motion. But these two forces will make a couple. A torque will act on the dipole. The expression of the torque is P cross E. If you open the cross product, you can write that torque is PE sine theta. This torque will try to rotate the dipole. This torque will try to rotate the dipole. The dipole will rotate until it aligns along the electric field. So the torque will try. So the torque will try to align dipole along the. Now it's a separate discussion that dipole will get aligned or not. Dipole will try to align along the field but will keep on oscillating. The dipole will keep on oscillating and this particular oscillation is SHM that we will discuss in the next numerical. But for the time being, if you place a dipole in a uniform field means field where both magnitude and direction of field does not change with time. Field in which magnitude and direction does not change with position is a uniform field. If you place a dipole in a uniform field, net force on dipole is always 0. It's irrespective of the angle theta between the dipole moment and the field. But the dipole will experience a torque and that torque is P cross E or P sine theta. This torque will try to align the dipole along the direction of field. Now you can discuss 3 cases here. Case 1, if P is parallel to E. See, if two vectors are parallel, then the angle between them is 0 degree. You can calculate torque. The torque will be PE sine 0, which is equal to 0. So force is always 0. Now in this particular case, torque is also 0. 0 degree means this is electric field and your dipole is along the electric field. Both force as well as torque is 0. That means your dipole is in equilibrium. This condition is known as the condition of stable equilibrium. Case 2. Because if I disturb the dipole, it will ultimately come back to this position. Case 2. If P is anti-parallel to you, if dipole moment is anti-parallel to electric field, in that case, theta is 180 degrees. When you calculate torque, the torque will comes out to be PE sine 180. Sine 180 is 0, so your torque is again 0. So anti-parallel means this is your electric field, but your dipole is in a direction which is opposite to that. This is also an equilibrium, but we call this as unstable equilibrium, because if you disturb this dipole, it will not come back to its original position. Original position means when it is anti-parallel. When you disturb the dipole, it will rotate and become parallel field, or at least it will try to align itself along the direction of electric field. If you disturb it, it will not go anti-parallel. It will try to go parallel to the field. That's why we don't call it stable equilibrium. We call it unstable equilibrium. Third case is if P is perpendicular to, if both P and E are perpendicular, that means torque will be PE sine 90. Sine 90 is 1. So you can say in this case, the torque is PE, and this is the condition for the maximum. So in this particular case, your torque will be maximum. Now, along with the torque, one can also discuss the potential energy of the dipole. The potential energy and the work done to rotate the dipole. Let's discuss that position. Although this potential energy is in chapter 2 of NCERT electric potential, but since we are doing torque here, we'll discuss potential energy also. Now, if you want to calculate work done, see, this is your electric field. This is your dipole moment. Initially, your dipole is at angle theta 1. Torque will try to rotate the dipole and to align it along the field. But if you want to bring this dipole against the field from theta 1 to theta 2, then you have to do some work done. Work done by external force, or I should write it by external torque, in rotating dipole from theta 1 to theta 2. If you want to rotate the dipole from theta 1 to theta 2, then you need to do some extra work done, external work done. Then that external work done is minus of PE cos theta 2 minus cos theta 1. And this work done gets stored in the form of change in potential energy. So this work done by external source in rotating dipole from angle theta 1 to theta 2, that gets stored in the dipole in the form of potential energy. This is potential energy difference. Potential energy difference. So what is potential energy difference? Potential energy when the dipole is placed as theta 1 subtracted from the potential energy when the dipole is placed at theta 2. So this delta U is U2 minus U1. But instead of work done by external torque, if you want work done by electric field, then work done by electric field is just negative of work done by external torque. So work done by electric field is negative of work done by external torque. Or you can simply calculate potential energy also. If you want to calculate potential energy, then potential energy is simply minus of PE cos theta, or you can write this as minus of P dot E also. So let's summarize all these things. So when you place the dipole in a uniform electric field, net force on the dipole is 0. It will experience a torque which is P cross E or PE sine theta. If you want to rotate this dipole from some angle theta 1 to theta 2, then work done by external torque is this minus PE cos theta 2 minus cos theta 1. And this work done is equal to change in potential energy also. Similarly, if you want to calculate work done by electric field while you are rotating the dipole, then it's just negative of work done by external torque. If you want to calculate potential energy, not the difference, then it's minus of PE cos theta or minus of P dot. Here also, in the three cases, along with the torque, you can also calculate potential energy. Like in the first case, your potential energy is minus of PE cos 0. So it's minus of PE. This is the minimum value of potential energy. So in stable equilibrium, your potential energy is maximum. If you want to calculate potential energy here, this is PE minus PE cos 180. Cos 180 is minus 1. So this will be plus PE. Here your potential energy is maximum. If it is perpendicular, then you can write that your potential energy is minus of PE cos 90, cos 90 is 0, so potential energy is 0. So this is how we can calculate both the torque as well as potential energy in different cases. Let's note it. Now we'll start some numerical solution. Written?
Yes, sir.
Note this also. Just one second, please. Please tell me once you have written. Done?
Done, sir.
Done, sir.
Done, sir.
Done, sir.
Okay, now try this numerical. Try this numerical. Are you able to solve it? So this numerical is very easy. Only the language is a bit confusing. Say there are two separate cases. First case is up to here, then the second case is here, and this is the relation between the two cases. Pasna, answers? No answers, huh? Sorry. See, you have a electric field. Electric dipole has a fixed dipole moment P, which makes an angle theta with respect to x-axis. Electric field is also along x-axis, so you have a field. This field, the name of this field is E1. This field E1 is along x-axis, and in this field you placed a dipole having dipole moment P, and this dipole is making some angle theta with the field. The torque acting on the dipole is T1, that could be written as tau K1. So the expression of torque will be P E1 sine theta. Now, what is E1? E1 is EI cap. Direction of E1 is along x-axis and magnitude is I. So instead of the magnitude of E1, I can write E. So this is PE sine theta. Is it clear up to here?
Yes.
Okay, now let's
Yes,
come
sir.
to the second case. When subjected to another electric field E2 or root 3 I cap, it experiences a torque. Now the next field is root 3 E1 J cap. The next field is along Y axis. This is the next field, E2. So if a dipole is making an angle theta with E1, which is along x axis, then what will be the angle between dipole moment and E2? What is this angle now? Ira, what is this angle?
90 minus theta.
90 minus theta. So you can calculate T2 here. P dipole electric field is E2, sine angle between them is 90 minus theta. And Vasna, how much is sine 90 minus theta?
Cos theta.
Cos theta, that is equation. Now the next is T2 is minus of T1. These both have opposite directions and equal magnitudes. So you can write that T2 is equal to T1. You can write that TE2 cos theta is equal to, and we also have to write the magnitude of E2. What is the magnitude of E2? E2 is root 3 even. So that's P root 3 E1 cos theta. And how much is E1? E1 is equal to E. So you can simply write this as P root 3E cos theta. Yes, are you able to follow it? Is it clear up to here? This equation
Yes,
number
sir.
two. Now, since T2 is minus of T1, means they have opposite direction and equal magnitudes, just compare them. So P root 3 E cos theta is equal to PE sin theta. P will cancel this P, E will cancel this E. Your root 3 is tan theta. And your theta will be 60 degrees. So 60 degrees. Note it down. There's one more type of question that is on SHMs. Do it, then we'll discuss SHM. Tell me when you're done. Please try not to copy the entire numerical. You can do it yourself.
Done, sir.
So the next question is on SHM. So Basna, what is SHM? Mira, what is SHM?
Simple half.
And what is simple harmonic motion? How will you decide whether a motion is simple harmonic or not? So for a motion to be simple harmonic, the first thing is it should be oscillatory. If a motion is oscillatory, then it can be simple harmonic. But if it's not oscillatory, then it can never be simple harmonic. So simple harmonic is a special case of oscillatory motion. Oscillatory motion which satisfies following conditions. So the first condition is restoring force or restoring torque acts on it. A restoring force or a restoring torque should act on it. The first condition for a motion to be simple harmonic. Second condition, this restoring force or torque, this restoring force or torque should be proportional to displacement from mean position. If it is linear, then it will be linear displacement. If it is an angular SHM, you are taking torque, then this will be angular displacement. Third condition. Restoring force or restoring torque should be directed towards mean position. Should directed towards mean position. So if an oscillatory motion is satisfying all these three conditions, then you will call that oscillatory motion as simple harmonic. Or you can just write tau. If it is angular, then you can write as tau is minus of k theta. This tau is the restoring torque. Theta is the angular displacement and k is a constant which is known as spring factor. If it is linear, then instead of torque, you will be having force and it's minus of kx. This is for the linear motion and this is for the angular motion. Once you have this equation, you know k, you can calculate omega. Omega is root over ky. And omega is related to time period also. Omega is 2 pi. Now, so this was basics of SHM. Now see how we'll use this SHM into the dipole. Question says, show that motion of electric dipole in uniform field is SHM. So we take a dipole. This is electric field E. Then we place a dipole P at an angle theta to the electric field. Now this electric field and exert a torque on the dipole which is PE sine theta. This torque will try to align the dipole along the direction of field. Now this torque and this angle theta are in opposite direction. You can say that earlier the dipole was along the field, then we disturb it by an angle theta. So this angle theta is anti-clockwise. A torque is acting on the dipole which is clockwise. This torque is trying to restore the equilibrium position. So that's why I'm putting this negative sign, because this torque and theta are in opposite direction. Torque is clockwise, theta is anti-clockwise. At this point, it's not SHM, because for SHM, your sine theta, they should not be sine theta, they should be theta. So in general, this motion is not SHM, but if you take small angle approximation, then you can say that sine theta is approximately equal to theta. Then you can say that restoring torque is minus of PE theta. Then you can say that restoring torque is minus of K. So instead of K, you have PE now. So this is what you're supposed to calculate, PE, K, the value of K. Once you have K, you can calculate omega. Omega is root over K by, here instead of mass, we will be using moment of inertia. We will be using moment of inertia. So this omega will be root over PE divided by I. So once you have omega, you can easily calculate your time period. Time period is 2 pi by T, which is root over PE. Now you will get many questions on this thing. The question gets modified over this point at moment of inertia. You can calculate moment of inertia about different type of axes. So you have varieties of question due to this moment of inertia. So I'm considering all cases. Let's calculate the moment of inertia of dipole. Moment of inertia of dipole. So you have a dipole, it have two types of charges. One is negative charge, this have mass m, another is positive charge. Since both the charges are identical, they will be having same mass, same type of particles. You can calculate moment of inertia about the center also. Say this is A and this is A. I'm taking A because the total length of the dipole is 2A. So if you're calculating moment of inertia about center, then this will be the relation of moment of inertia for a point mass is mr square. So here the moment of inertia is ma square plus ma square. This is about the center. But if you are supposed to calculate moment of inertia about n, let's say I ask you to calculate moment of inertia of dipole, this is mass m, this is mass m. I ask you to calculate about this mass. Upasana, what is the perpendicular distance between this mass and axis which is passing through one end? See, axis is passing through the mass, so there is no perpendicular distance between them. The perpendicular distance is 0. And the length of the dipole, if I say it's 2a. Mira, what is the perpendicular distance between this m and axis of rotation?
2a.
2a. So, what will be the moment of inertia of this m about this axis? It's m into 2a square. And what about this? M is over the axis only, so the perpendicular distance is 0, so m into 0 square. So the type of questions that you will get on oscillation will have variation due to this term only. In some numericals, you are supposed to calculate moment of inertia from the center of dipole. In some numericals, you are supposed to calculate moment of inertia about it. No return. Just tell me once you have written.
Done, sir.
You can get the question on SHM in Coulomb's law also.
Done, sir. Done, sir.
This is the most crucial part, the moment of inertia. Always check question whether you're supposed to calculate moment of inertia about the center or about the end. Both are different values. And instead of 2a in some questions, the length of the dipole is L is given. Sure. After this, there is one more topic, which is dipole in non-uniform electric field. Upasna, so if I place a dipole in uniform field, what is the net force on the dipole?
0.
0. But if I put this dipole in non-uniform field, electric dipole in non-uniform field. If I place this dipole in a non-uniform field. So what does non-uniform field means, Mira?
The field is not uniform at all points.
So the magnitude or the direction or both can change. So let's call this as a non-uniform field. This is the magnet field is E1 here. This is E2 here. This is the dipole. This is minus Q1, minus Q. This is plus Q. Now, since at both the points, the magnitude of field is different, so you can see that force will never cancel out. The positive will experience a force which is QE1. The negative will experience a force which is minus of QE2. The net force will be QE1 minus QE2, which is not equal to 0. So the net force on the dipole is not 0. There is some net force which is acting on the dipole. So this will have some translation. So it can move along positive x-axis or negative x-axis. Then there is a torque on the dipole, and that torque is P cross E. So this will have rotational motion also. So dipole will have both the translational motion as well as rotational motion. So combined motion will be the sum of translation plus rotation. So the net motion is the sum of both translation as well as rotation if your dipole is in a non-uniform electric field. Note it down, we'll do some numerical solution. In uniform field, the dipole will just have simple harmonic motion. There won't be any translation, but in non-uniform field, it will have a combination of both translation and rotation.
Done, sir.
So there's one question over it. Yeah, that's the question. This question is also in NCERT. Just first read the question and draw a rough sketch. Then we'll solve it. You have 2 minutes, just read the question and draw the rough sketch. Where is positive charge? Where is negative charge? What is the direction of field? And you can take this as your z-axis, this as y-axis, and this as x-axis. First, draw a rough sketch. Okay, so let's start. In a certain region of space, electric field is along z direction. So your electric field is along z direction. The magnitude of field is not constant, but increase uniformly along z direction at the rate of this. So Upasana, field is uniform or non-uniform?
Non-uniform.
Non-uniform. This is the rate of change of field with distance. Now this rate, this term rate here is misleading, because rate usually means change with respect to time. Here field is not changing with time, it's changing with position. As you go along z-axis, the field will increase. After every 1 meter, the field will increase by 10 to the power 5. You're supposed to calculate force and torque experienced by a system having total dipole moment of 10 raised to the power -7 in negative z direction. That means your dipole is placed in this way. This is how your dipole is placed. This is minus q and this is plus q. This is how your dipole is placed. Now you're supposed to calculate the net force on the dipole. So the net force on the dipole is, although there's a lengthy derivation, I'm not going into the derivation. I'm writing the direct result. To get force in these type of cases, the expression is dipole moment into dE by dz. So here the dipole moment is 10 to the power minus 7. You can use this as a standard result. dE over dz is 10 raised to power 5. So it's 10 raised to the power minus 2. But the important thing is direction of force. In which direction the force will act. Force can act along positive x-axis or negative x-axis. For the direction, what we will do, this is minus q charge. Field is along positive z-axis. Negative charge will experience force in the downwards direction. Let's call this as F negative. The positive charge will experience force in the direction of field. That's F positive. The net force will be due to the subtraction of these two forces. Now we have to decide out of these which one is the stronger one. So field is acting along positive z-axis. So the field over the negative charge is stronger as compared to field due to positive charge. Why field at the position of negative charge is stronger? It's because field is increasing along positive z-axis. So F negative will be greater than F positive. So the net force will be along negative z-axis. And if you want to calculate a dipole moment, see, dipole moment and field are anti-parallel. When they're anti-parallel, then torque is 0. P E sine 180 is 0. The torque is 0. Yes, is it clear?
Yes, sir.
Yes, sir.
Okay. You can take this key. This is also into NCERT. This is back exercise of NCERT. Remember this as a direct result. F is P dE over dz. Push.
Done.
Okay. So this is about dipole, electric field and all. The next topic is Gauss law. That will start in the next class. Maybe I'll take one more class tomorrow. Then we'll try to finish the Gauss law, the electric flux and Gauss law. Today you have test also, no?
Yes, sir.
Okay. Okay, we'll stop here. Tomorrow we'll take one more class of this electric flux and Gauss law. All start. We'll stop here. Okay.